Hello and welcome to Emulating Risc-V in a high-level language. Today we're going to implement command line. What does this mean? It means that our emulator will have access to the command line that was typed when when the emulator was started. And this allows us to provide parameters to the program that we're running. For instance, if we wanted our Risc-V program to uh, get a file name from the outside, from the user, this is one way to accomplish that. Before we start implementing the command line support, however, I'm going to implement a utility class that will become handy. And the reason for this is because we're doing a lot of memory manipulation this time, and it becomes harder and harder to understand what the program is doing without some sort of debugging tools. So this will be the first debugging tool that we'll be implementing for our emulator, and there will be more as the difficulty of the programming keeps increasing. So the tool that I'm going to be writing is a memory dump tool, and memory dump tools are very commonly used by low-level programmers when you want to see the exact contents of memory, which is what we're going to be doing today. We're going to be manipulating low-level memory. So let's start by going to our unit tests, and let's add the specification to the unit tests that will guide us in the implementation of our new tool. So I'm going to create a new test, a file or a test fixture called hex dumper tests. And this class lives in the namespace rbfun unit tests. And it's a test fixture. So what do we want to do here? Well, the first thing we want to do is make sure that when we dump, well, let's sketch our uh, sketch our unit test. We want to test that if we dump a line of memory, we get the expected output. So I'm going to create a chunk of memory, um, and it's going to be the following bytes. Actually, let's do this. And then we'll just write some bytes. And I will be using the numbers starting at hexadecimal 40 and then 41 and so on. In fact, that's going to get tedious. Why don't we just generate them? So we'll call enumerable.range, and we'll start at 40, and we'll do hexadecimal 10. Now, for those of you who are familiar with the ASCII encoding, you'll recognize this number as the ASCII code for the @ sign. And after 40 for hexadecimal, then comes 41, which is the ASCII code for an uppercase A. 42 is uppercase B, and so on. So what this will generate is the ASCII codes for the first 16 characters in the region of the uppercase characters, in addition to the @ sign, which will lead them all. So this will give me a list of integers, but now we need to convert them to bytes. So we'll call select and take each one of these ASCII values and then convert it to a byte by just stripping out the high part. This returns just a single byte. And then we do that for each one of those integers, and then we convert the resulting enumerable to an array. And then here we might as well use the collection expression to generate this. So here we now have an array of 16 bytes starting at 40 and of length 16. That's 10 hexadecimal, and it will have the ASCII codes for the first 15 letters of the alphabet preceded by the @ sign. Okay, great. So now we have our data. Now we want to write a class called dumper or hex dumper that will dump this in the way that we want. So we'll have the specification that we want to dump the output into a text stream. So let's create a text stream, and we'll call it a string writer. So string writer is a subclass of the or derived class of the base class text writer. And what we'll do then is we will create a dumper, which doesn't exist yet, and we'll pass in the memory that we want to dump. And then we will say that we would like to dump. Actually, let's make this a memory. Let's make this more interesting. We'll create a memory. And then we'll tell the memory, I want you to put that chunk of bytes at address, this address. And it's readable memory, like that. So there's our chunk of memory. And now what we want to do is feed that memory to our hex dumper. And then we want to ask the dumper, please dump the memory starting at address, that one. And then give me the whole 16 bytes and put the result into the string writer that I'm feeding you here. And then at the end, we will assert that the contents of the string. So let's extract the contents of the string writer. And then we're going to assert that this is equal to the expected. And what is our expected? Well, our expected would be the following output. First of all, we want to see the address. So we want to see the address properly write justified in a field of 8 characters, like that. So this corresponds to this address right here. And then for each one of these bytes that we are writing, we want to see its the representation in hexadecimal. So we expect the first one to be a 40 and a 41, a 42, 43, 44, 45, 46, 47, 48, 49. And then because we're in hexadecimal, we get a 4A, a 4B, a 4C, a 4D, 4E, and 4F. And then, separated with a space, we want to see the representation of these characters in ASCII. So A, B, C, D, E, F, well, J, H, I, J, K, L, M, and then N, and finally O. And then at the end, we want a new line. So we want to have whatever our operating system's environment a representation of a new line is. So on Windows, this will be a carriage turn and a light field. On a Unix platform, this would be just a new line or line feed. So this is what we expect to get out, and now we have the test. So now that we have to write the code. Piece of cake, right? We go now to our assembly here, and we will put it here. We'll add a file called hexdumper, and then we'll start coding. All right, so let's go back to our unit test and see, can we find this? We need to add a reference to RVFun. All right, let's build everything just to make sure. Okay, so here we go. And now we need to create a constructor because we need to feed this memory to the constructor. So let's do that. So now we have this, and let's make that read-only because we'll never change it. And then we need to implement the method dump. So let's generate that. And let's adjust these because these should be unsigned. So this is the unsigned integer that will have the address that we want to start dumping at. Let's call it address. Well, let's call it address for now. We'll figure these details out later. And then we have the length, the number of bytes that we want. And then instead of a string writer, we want to use a text writer because we want to support the capability of writing to to the console or to a file. Okay, all right, let's try building everything. And now we should build, but of course our unit test will not pass because we haven't implemented the dump functionality yet. Okay, so let's do this strictly by the book. We will run all of our unit tests and we expect one failure. This dump should now not work. And indeed it doesn't. So, and of course the issue is because you haven't implemented the method yet. Fine. So let's start implementing this. So we want to first display the address. So let's do that. Take the writer and we'll say write, and then we'll pass in a format string, or we'll format the string the way we want it to look like. So we'll say take my address and format it in a hexadecimal field of width 8. So this will generate 8 characters. Okay, great. And then what we want to do is we want to render the memory 16 bytes at a time. So we have this line length of 16 bytes. So let's declare a constant. And we'll call it line length. And it's 16 bytes. That's 10 hexadecimal. And so what we'll do now is loop through all the bytes in memory, starting at this address. And we'll set up an ending address. So let's say adder end is equal to address plus length, like that. Now we're going to do a for loop where we start at, we'll create a new variable called a, I suppose. Start at a, and a will start at address, and then it will continue until address end. Adder end. But then what we're going to do is we're going to be incrementing this a, which is a uint, by the line length. So we're incrementing a in steps of 10. In fact, let's call this adder line because what this is going to be the address of the start of the line. Let's do that. So this is adder line. This is the address of the current line. So then we increment it by 10 hexadecimal each time. Let's get rid of this exception as well because we don't want to keep throwing. Okay, so we need to move this inside of our loop because we want this to happen at every line. So now that we are starting to write our line, now we need to go through our 16 bytes. And let's do this way. So we'll have a uint, which is I, is starting at 0, and then I is I less than line length, increment I. So this will go through each individual byte. And what we'll do now is we'll say w.write, and now we'll write a space in front of each byte so that they're not all glommed together. And then for each byte, we will write it, we will read the byte first of all. So we'll say var b equals memory.read byte at address adder line plus I. Okay, and that will give us the byte. So now we have a byte, but we need to render it as a hexadecimal number. And I want it to use up 2 character positions when it renders. Good. Okay, so this will write out all of those. And then where we repeat the loop, but this time we're going to be writing out the ASCII equivalents. And so instead of writing the data out as a byte, we will now check to see if this byte B is printable. And inside of the traditional ASCII range. Now, if you're unfamiliar with this, it means that we need to restrict the bytes that we are writing out to be between the range of hexadecimal 020, which is the same thing as a space. That's the ASCII code for a space. And we want to avoid uh, printing characters that are larger than or equal to this hexadecimal value, which is the delete symbol in ASCII, which is not a printable character. So if the ASCII value is between 20 and 7F, we want to print it out. If not, we will replace it with a substitute character that just indicates that this is not a printable character. And traditionally, the dot is used to indicate non-printable. So we'll check to see if the character B is uh, between hexadecimal 20. Oh, got the logic all screwy here. If it's larger than or equal to 20 and it's less than 7F, then this is a printable character. In that case, we'll write the we write it out as a character. But a byte is not a printable character, and so we need to tell C# and the .NET runtime that we want to treat this number as a character. So we just simply cast the byte value to a character. Now this will turn B into a UTF-16 code point. That is the Unicode code point. But it so happily happens that the first 127 or 128 code points of Unicode coincide with ASCII. So this will just convert this byte value, which is the number, into a character, which is something that the .NET runtime will then display on screen as a character value. If, however, this is not the case, then we will write it out as a dot. Okay, good. And then we are done. So let's see if this works first try. And it fails. Now, why did it fail? It failed. Well, I'm still haven't gotten the hang of how to do this. So let's just put a breakpoint here in our unit test and debug it. That will give me the real truth inside the debugger. So, what is actual? Oh my goodness. I have a bug. Look at that. Notice, however, the last part did okay. It rendered it correctly, but our formatting code is incorrect. So let's fix that. So I'll go back to my hex dumper code, and there's a $sign missing. Yep, it's right there. There we go. Okay. Oops. Yep, didn't want to do that. Now we're starting the program. Doesn't matter. It will just run and stop. Let's stop you right there. Okay, let's go back to our unit tests and let's run it. Let's just run this one because it's this one particular test that we want to test. Ah, I see one issue. We'll still get a bug, and that's because we don't have a carriage return and line feed at the end of our line. So after these two for loops have completed, then we want to say text writer write line. So this will terminate the line. Let's try that again. Okay, still not happy. All right, let's debug this again and see where the issue is. So actual has a new line, expected has a new line. Ah, there's a missing space between the 4F and the @ sign. That's easy enough to fix. So right here, we will write a space to separate the two sections. All right, let's stop the debugger, go back to our tests, and let's run it. All right, still not happy. So our actual string has all the numbers. The expected string. Oh, I made a mistake. How about that? Brings up the philosophical question, what if your unit tests have bugs? How do you find them? You write a unit test for the unit test, of course. Okay, great. So we have successfully printed a single line of code. But I want another test because I want to be able to start dumping in the middle of a line, and I want to stop dumping at the end of a line. And our little unit test isn't capable, or our hex dumper class is not capable of doing that yet. So we need to add support for that. So I'm going to call it partial line, this new unit test, and it will use the same setup. So why don't we just migrate this code into the same constructor. So we'll just move the memory that we created here. Okay, nice. And then why don't we call that constant some nice private um, memory address. Why not? And then we'll just use that here, just like so. Now we need to create a member variable called memory. Let's make that a read-only field. Nice. So now we can access that from over here. And then let's call this memory address. Okay, so I'm going to just blithely copy and paste this code. And now we're going to do a different string. We're going to start dumping the memory, but starting at an address that is 2 in. So I want to skip 40 and 41 and start displaying the bytes at address 42. However, so let's just overwrite those with spaces. So let's undo that. Undo this using the insert key like that. That's what I want output. I also want to skip the printing of the last two words like that. And then I want the address that we're rendering to be the start address. So that 1002 matches that 42 that we see there. However, I still want all my columns to line up nicely. So this will look nicely if we have a larger range of lines. But this is the logic that we want to implement. So clearly our code that we have written so far doesn't know how to handle this, so we need to implement support for handling this particular kind of um, a case where we have an address that is not an even multiple of a line, and the number of bytes does not end at the end of the line. All right, so let's run this, see what we get. We expect an error. Oh, there it is. Okay. So what do we do to fix this? Well, let's go back to our dumper over here. And I'm not sure why we're getting these errors, but let's start by reviewing the code. The first thing that we want to do is we want to keep the logic that writes the address. So if we get an address that is offset by 2, we still want to write that address here. But we want the line address that we're starting at to be this address right here, the one that ends with a 0. We need to get rid of that last 2 because we want to start the address that we're looping through to be aligned at this address right here. Even though we won't display any bytes, we want the address to be aligned there. So how do we do this? How do we accomplish that? We take the address that we were given and we align it by getting rid of the lowest byte. And a quick and dirty way to do this is to take the AND operator and use it to mask the address like this. Okay, so what is this doing? Well, it's taking the address and it's taking the logical AND of this expression here, which is, recall that the hexadecimal F is 4 ones. This is a whole lot of zeros followed by 4 ones, but then we use the complement operator to switch all the ones to zeros and all zeros to ones. So this becomes a mask containing a lot of ones in the beginning and then 4 zeros at the end. And if you recall, when you do an AND, the bits that are zero will not survive. So what the net effect of this is that it will strip out the lowest nibble, the lowest 4 bytes of the address, and that will become our address line. Now when we write our bytes, we have to check to see, first of all, if this address is valid within the range that we want. If it's not, then we just write spaces. So what we'll do is we'll say that the um, adder A, let's compute that. This is going to be this expression. Now, if A is less than address, the starting address, or if A is larger than or equal to address end, then we're out of range. And so in that case, what we want to do is write just 3 spaces because we're out of range. Otherwise, we read from that memory and then we write that memory. Good. And we need to do the same thing over here. We need to say var A equals adder line plus I. And if that address is out of bounds, then we write a space. Otherwise, we do what we did before. Like that. Do we believe in this? Let's see. Oh, let's go back to our hexdumper test. We also need to change our test to exclude the first 2 letters or ASCII characters and the last 2. All right, let's give that a try. Okay, so we're getting an exception. Let's run this under the debugger and see what the problem is. Okay, let's look at the call stack. So we're trying to read a byte at address. Oh. All right, so we've gone beyond. Oh, okay, good. Um, let's see where that is actually getting called from. So we're trying to access an address that is out of bounds. Fair enough. Why did that happen? Why did that happen? Well, we check to see if adder end. What is adder end? Okay, adder end is incorrect. Adder end should be. Oh, it's a bug in our dump. Our dump is incorrect. We only want to dump this many bytes. Hexadecimal C, which is 12 bytes. Yeah, so again, there was a bug in our unit test. All right, let's fix, or let's run that now and see if that fixes the problem. Lovely. Okay, so we now have a tool that allows us to look at the contents of memory, and this will become very handy now that we can, now that we are ready to implement the command line support in the emulator. Let's go ahead and um, let's go ahead and add the changes. And just have them nice and saved away. Now we're ready to implement our command line. So let's go back to our main program and look at how the main program sets up for execution. So the first thing that we do is we take our assembler and we assemble a program that we wish to execute. And then at the end, we call the linker. This linker generates a memory image of the program that we wish to execute. And then we create our OS emulator. We create a stack segment, which is disjoint from the program segment. This is the work that we did last time. And then we create the Risc-V emulator itself. We pass it in the memory and the OS emulator and the starting address, the place where we wish to start executing. And then we set up a few registers. Probably the only one that we need to set up correctly is the stack register, and we set it up so that it points to the last addressable word in the stack. So notice how we say take the stack address, go to add stack size to it. This would be the first byte after the stack, and then we back in 4 bytes because our stack pointer is pointing to words that are 4 bytes wide, and so that the stack pointer will then be pointing at the last addressable word in the stack, and then we run the emulator. So what we want to do now is think about how do we get the arguments, the command line arguments into our memory. Well, first of all, how do you get the command line arguments from the .NET runtime? Well, that's easy enough. This is the main program, and the main program has a predefined variable called args, and args is an array of strings. Those are the command line arguments. So, however, because we want to be doing a lot of testing, we're going to be setting up this so that if there are no args, we're going to initialize args to be a set of well-known strings. So if the args.length is equal to 0, then we are running in debugger. And so what we'll do is we'll set args to be equal to the string hello and world, following tradition. And then otherwise, the string will be just args itself. So what this will do is we'll initialize args to be args.length. Okay, now, having done this, we now have to think about how do we pack these into memory. And there are a few challenges that we have to do here. The first one is that these strings are not something we can just hand off to the Risc-V emulator because they're not actually in memory. And the second issue is where exactly in memory do we put these? And we have 2 segments of memory now. One of the segments of memory is the one that the linker created when it assembled our program, or linked our assembled program. And the other one is our stack that we just created, which also happens to have readable and writable memory. And it turns out that in a lot of operating environments, there is an expectation that the command line arguments are writable. Not all of them, but it's convenient for us to say, well, why don't we just put the arguments at the very, very end of the stack? I mean, we have a pretty generous stack here. The stack size is what? 4 kilobytes. So we have plenty of room to put in these 2 little words at the very, very end of the stack. So what we could do is decide to squash these 2 arguments at the very end of the stack. And then we now have bytes in memory, and we need to get the address of those bytes back to the emulator so that the emulator has them in the registers that it expects them to be in. And we'll come back to that. But let's first start by flattening out these strings and placing them in memory. So to do that, we're going to create a method on the OS emulator, and we're going to call it initialize stack. And we'll take this piece of code that we already have, and we will pass it in, and then we will, in addition, then arrange for the stack the command line arguments to be placed at the very end of the stack segment. So let's do this. Let's call OSMU, and we'll say create stack segment, and we'll pass in the stack address and stack size, and then we'll pass in the arguments that we want to tack on to the end of the stack segment, and we will take this piece of code and put it inside. Now when this is done, what we want to come back, we need two values to come back out of this. The first value that comes back is going to be the stack pointer. So let's call that one the first one. So this will be stack pointer. The second one is going to be the pointer to the first argument string. So we'll call that arg pointer. And then finally, we will want the argument count. So arg count, like that. All right, now let's implement this method. And that method is over here, and this is going to be a uint, this is going to be a uint, and this is going to be an int. Okay, so here is our new method, and we'll take the code that we already had before, and let's pass in the stack address and the stack size and the access mode. Okay, so the next job we need to do now is take the command line arguments, args, and we need to place them in memory. So to do this, we need to do two steps. The first step is to write the actual contents of the string into the memory. And what we'll do is we'll go from the last argument to the first argument. So we'll walk the arguments backwards. So we'll start with the world and then write the hello into memory. So let's write a method called store arguments. And we'll pass in the arguments. And what this function will do is it will place these arguments in memory, but also it will end up giving us an array consisting of the places where those strings ended up going in memory. And we need those because we need to build another data structure in memory, which is the pointers to these strings. So we'll call these arg addresses. And then after those argument addresses are stored, we're going to say store address vector or list. Let's call it vector. Arg addresses, like this. And then we need to return from that the beginning, the location of the argument vector. So this will return, so this will store a bunch of pointers into memory and then return to us the address of the first pointer that we stored in memory. And then the stack pointer is going to be started at the address below that pointer. So we'll say that the stack pointer is equal to the argument pointer minus 4. So the layout in memory will be, if you allow me a crude sketch, is starting at the end of memory, we will see something like hello and world. And then before that, we will see two pointers. This will be, the first pointer will be something like this. The second one will be something like that. So these will be referring to the hello, and this will be referring to the world. And then finally, this number itself is in memory. Maybe this memory location is 0xF00 or something. So this is the value that we want to return. This points to this, and this points to this, and this points to this. So we have a nice little data structure in memory, but we want the pointer to point back to the beginning of these two addresses in memory here. So this is the memory layout that we're aiming for. Okay, let's implement these two methods. And then also let's return the value stack pointer and arg pointer and the number of arguments, which we'll just copy from args for now. Like that. Great. Okay, so let's now loop through those strings. And what we'll do is we'll store them in memory going backwards, as I said. So we also have to create a list of pointers. So we'll hang on to the places where we store those strings. So let's start by going backwards. Oh, and we'll also create our array. So for each string that we got from the .NET runtime, we're going to create a string in memory, or write the bytes of that string into memory, and then remember where those bytes were written. Now we're going to be going backwards through our arguments. So we'll start with I equals args.length minus 1, and then I is larger than or equal to 0, and then decrement I. So this is a typical C# backwards loop. And so what we do then is we grab the string, the argument, and then we ask the .NET runtime, could you please measure how long this string would be if I were to convert it to ASCII or UTF-8 bytes. So we'll say encoding.utf8 get byte count, and then we pass in the string. But then also, we need to account for the fact that the strings in our emulator are all terminated by the null character, the 0 character. So we need to add another extra spot to be able to store that byte. So this is the number of bytes, the count of bytes that we need for this particular string. Now, where do we start allocating? Well, we have to have a value which is where we start allocating. So we'll say uint address, where we wish to store our values, and then we'll pass that in. That's going to be stack address plus stack size, so the very end of our stack segment. So what we're going to do now is we're going to compute a new address, which is the address of the string that we wish to store. That's adder str, and that's going to be the adder that we are currently working with plus or minus CB. So this will start at this address and then back down this many bytes, which will give us space to put the bytes that constitute the string plus an additional 0. Now we need to get those strings. So the first thing we need to do is create a place in memory where we can store the string. So what we'll do is we'll say the span is the memory get span starting at the address, and then the length is the count of bytes. That's the place where we want to store our string, and we want that to be access mode read write. Now that we have a span, we should be able to copy to it. So how do we do this? Span dot. Oh, we can do copy to. Perfect. So we'll now grab the bytes for the string, and that's going to be encoding .utf8 get bytes of the string s. And now we have those bytes, and now we can say span copy to no, bytes as span copy to the other span. And then we need to write the terminating 0, so we'll say mem.writeByte at adder stir plus cb minus 1. And we'll write a 0 there. That's the byte value of 0. And we need to cast this to an int because of decisions. A uint. There we go. So this should write the byte, the bytes that make up the string into that address in memory, and then we simply repeat this, decrementing the adder as we go through each iteration of the loop, and storing the strings. Okay, great. And then at the end, we need to return, we need to store the address that we generated here. Let's store that into the result. And we'll use the same index as the original strings, so we keep the order of these pointers in the same order as the order in the arguments that were passed in. And let's cast that to a uint. Okay, finally we return our result. Okay, so let's do a little fun thing here. Actually, let's continue. We'll keep going, assuming that this code is working correctly. I'm hoping that it is. It's very linear, but there are always the possibility of bugs. Okay, now that we've stored the arguments, now we need to store the addresses of those strings in memory as well. So we'll take a uint of addresses, the argument addresses. And now we recall that we have a layout in memory where, we have the end result we want is a pointer for the first argument, a pointer to the second argument, and then somewhere else in memory, here we have the arguments. So arg1 and arg2. So here's the difficulty. These strings can be any length. They can be from 0 to n bytes, where n is an integer, any integer. So it could be 1 or 2 or 3 or 4 bytes. But when we are storing pointer values in memory or words in memory, the Risc-V architecture, if you go by the most strict definition, will tell you that you can only store a pointer at an address that is evenly divisible by 4. Because if you don't, then if you try to read from an address that is not an even multiple of 4, the processor will throw an exception. And there are many reasons for why the processor does not want to read a 4-byte value from an address that is not divisible by 4. For one, it complicates the internal design of the processor. So when we are writing pointers in memory, we have to make sure that the pointer value, the value that we're writing into memory, is itself located in an address that is divisible by 4. If it's not, then we run into problems. So fortunately for us, guaranteeing this is quite easy, because all we have to do is take the address that we want to write on and make sure that the lower 2 bits are not 1s, because if they are, then we're not divisible by 4. So what we'll do is we'll take the first address in our list of addresses, and what we'll do is we will use the trick that we used before in the hex dumper, which is to strip off the lower 2 bits of the address. And that will guarantee that that address is divisible by 4, and that will make our pointers compatible. So what we'll do is we'll take the bottommost address and align it. So we take arg addresses of 0, and then we do the same trick. We take the AND of the of the this constant, the number 3, and complement it. So the complemented 3 constant will consist of a bunch of 1s followed by 2 zeros in the least significant position. And that, when added together with any other value, will mask out the lowest 2 bits and turn them to 0, which is what we want. So at this point, we now have an aligned address for our strings. But now we need to make room for these 2 pointers, which need to precede this address. Otherwise, we would be overwriting the 2 words that we already, or the strings that we've already written to memory. So what we need to compute is the location that precedes these 2 strings by the number of addresses in our address vector. At this time, I should also point out that if we want to adhere to standards with regards to argument strings, we are required to write a 0 at the very, very end after these 2 pointers. So after PTR1 and PTR2, there needs to be room for a null pointer. So when we compute the address of the beginning of this vector of pointers, we need to take into account that we have to have space for a null pointer. So in order to do that, we're going to compute the vector address by taking the aligned address, and from that we will subtract the number of arguments, but then also we'll add 1 to that. That will account for the spot that we need for this null. And then we need to convert all of this to an unsigned integer. And then we need to multiply that by 4. Because we are storing pointers, and so we need to make sure that there's space enough for each one of these pointers. So what this will do is it will compute the number of bytes that would be needed to store this many addresses, plus an extra 1 for the null. And then we take that number, the number of bytes, and we subtract it from the beginning of the places where we stored the actual strings themselves, aligned down so that we don't end up with pointers that are not on aligned addresses. Okay, now that we have a position for where we want these addresses to be located at, now we start writing them there. So we're going to spin through our addresses for I equals 0, I is less than arg addresses. Let's create a pointer value, which will initially start at adder vector. And then for each pointer, we'll increment I, and we'll also increment the pointer by 4. Like that. All right, so there's our loop. So what do we want to do? We want to read the address that we want to write and then write it to memory. Sounds simple enough. So we'll say var a, which is the value that we wish to grab out of arg addresses. We'll grab that value, and then we'll take the memory and we'll say write this word. And the word that we want to write is the address that we just fetched, and then we want to write that at the address P. And I invert the order. This is P is the place where we want to write it to, and A is the value that we want to write to. And this should write a bunch of pointers into memory. And then when we're done, we will return adder vector to the caller. Okay, so if everything went well here, we should have stashed those 2 arguments in memory. So let's use our hex dumper to verify this. We'll go to our, let's go to our program, and here we will create a hex dumper. And we'll pass in the memory that we're using, and then we will ask it, so please dump the memory starting at stack putter, and the length will be stack address plus stack size minus adder putter or stack putter. So this will dump the memory starting at wherever the stack pointer is pointing at, and then the number of bytes that we wish to dump is the gap or the count of bytes between the end of the stack, which is this sum here, minus the beginning of the stack or the end of the stack, or well, the value of the stack pointer. So this will show us all the bytes that are located between the top of the stack and the end of the stack segment, if that makes sense. And we'll write that out to console out so we can see the contents. All right, and we need to cast this to an integer, apparently. Okay, that got rid of all the errors. Nice. Okay, so let's run our program and see if this gives us anything meaningful. Okay, so here's our hex dump. And let's look at the hex dump real close and analyze. I'll copy this to a spare buffer, and then we will... Oops. Okay, so we have a bug in our hex dumper. It looks like we're not incrementing the line address correctly. So let's fix that. Over here. Yeah, this is our problem. No, this is correct. Okay, we're doing a lot of double duty here. Address never gets updated, so okay, so let's... All right. Let's do this. Let's write address equals adder line plus line length. Hopefully that will fix the problem. Let's see if that indeed is the case. That is not the case. All right, that completely screwed us up. Let's see. So we're not allowed to add. Okay, let's rename this to adder min. Or address begin. Yeah, this is going to be a problem. Let's just dump address line for now. I think we're smart enough to realize when the address is not exactly at the beginning. So we'll modify our unit test to do that. That will fix the problem. Okay. There we go. So we have a problem. Look at our beautiful look at our beautiful code. The word hello has overwritten the world, so we've forgotten to update a pointer in our OS emulator. So let's take a look at that. Yes. So at the end of this loop, we have to update the variable adder so that it has the same value as adder stir. Adder stir is a uint, please. Okay. Run it again. And now we see a beautiful result. Let's copy this and analyze it in our command buffer. Let's clean this up a little bit. So we're focusing on... So there are two strings, world and hello. And notice that they're written hello world in the order that the arguments were passed in to the program. And the hello starts at address 40FF3. And these bytes over here are the little endian representation of that pointer, 400F3. The second pointer, or the second string, sorry, starts here, which is at address 40FF9. And here we see the second pointer at address 0400F9. And here we see the final null pointer that we are required to write at the end of our vector of pointers. So these are two pointers that are pointing to the individual strings hello and world, followed by a null pointer. And then here, this is the null pointer that we have, or the null value that's on the stack that our stack pointer is pointing to. So the stack pointer points to the 0, and then beyond that stack pointer we have our string vector, which is these 2 or 3 pointers, 1 pointer, 2 pointer, 3 pointers, and then followed by the actual strings themselves. So we have now successfully serialized the command line into a format that could be used by our emulator. So let's go back to our program now and make sure that those values that we have so laboriously computed get passed into the emulator so that it can start using these values. So what we want to do is make sure that register 2 gets the stack pointer. So instead of this now, we just say stack pointer. And we need to cast it to an int. And then the convention when you're starting a program is that the first arguments contain the count of arguments, arg count. And then the second argument is going to be the pointer to our arguments, arg ptr. And that needs to be cast to an int as well. So at this point, our emulator is ready to start using the arguments that are passed in to it. So in essence, we are now done with the implementation of arguments from the command line. At this point, I'm going to round off, but in our next installment, we're going to be using these arguments in an actual program. And it's going to be a very simple program. We're going to just echo the 2 strings that we're passing into the command line, but it will be an illustration of just how arduous assembler language programming can be, and also an explanation of why people invented more high-level languages. But it will be the first time that we write a really serious program in our little emulator. So until that time, I will say happy hacking and hope to see you back again.